And welcome to SanfordFlipMath. This is PreCalculus. We are steadily working through the PreCalculus book by Demana, Foley, Kennedy. We are in the 4th or 5th edition, depending on which version you have. And we are about halfway through, a little more than halfway through Chapter 4. And we've been spending a lot of time dealing with graphing trig functions, specifically sine and cosine. A little bit with solving sine and cosine equations. And now we are going to venture into the graphs and information about the rest of the trig functions. We've been kind of putting this day off because these are just less than fun. And most of you agree they're just, they're kind of ugly. They're kind of cool, but ugly. All right, so anyway, let's get to it. I want to spend a little bit of time reminding you of the unit circle stuff because I think it's very helpful to go back to this when trying to remember, values for sine, cosine, and tangent, etc., for different angles. So just a reminder that x is cosine, y is sine, and tangent is y over x. That wasn't a very nice way to write that, but it'll be fine. Okay, so tangent is like slope. You're going to hear me say that a lot. You've probably already heard me say that a lot. And we're just going to plot some points. So, like for instance, the tangent of 0 is 0. In fact, if you look right here, if I put y over x, 0 over 1 is 0. Okay. If I go to 30 degrees, also known as pi over 6, then the tangent is actually the square root of 3 over 3, which is about 0.577, something like that. Okay, so 45 degrees, pi over 4, the tangent is the square root of 2 over this, square root of 2 over 2 over square root of 2 over 2, which is 1. For pi over 3, and at some point I have to speed this up, square root of 3, which is about 1.732. And then let's do 90, also known as pi over 2. Well, up here, y over x, this is 1 and this is 0. Well, if I do 1 over 0, that's undefined. Okay, so tangent of 90 is undefined. And we've seen all of this before when dealing with the values in the big table that we did for the special angles and etc. Okay, so let's plot some points. So I'm going to number by 30s, I think, here. And you know that this is pre-calculus, so we're really not going to do this in degrees. We're really going to do this in radians. So 45 would be right in between there. Okay? All right, so here's 0, 0, 30, and 0.57. Well, I'm going to call this 1, 2, 3. Okay? All right, so 30 will be 0.577, a little more than half. 45 will be at 1. 60 will be at 1.732-ish. And then 90, well, 90 is not very nice at all. It's going to be an asymptote. Okay, I'm going to pop over to the calculator for just a second, and I need you to remember that the calculator is not a perfect tool, but it's going to help us at least get it. I really need you to get an understanding of what's going on with the shape of this graph first, and then we'll deal with the issues. Okay, so here's tangent. For ease of understanding what's going on, I'm doing this in degrees right now, and again, do understand that we're going to be working in radians, okay? And I really wanted to do the table. Now, I've numbered the table in kind of a weird way. I'm numbering by fives. If I go to table set, this is right above window, table set. I can start it at any number I want, and that little delta table, that triangle table, is the change on the table. So that's how it's counting. So if I go back to table, all right, so here are the numbers I was talking about. There's the 0.577. There's 1. Tangent of 45 is 1. Let's look at 60. Tangent of 60, 1.732. And notice these numbers are getting bigger and bigger until I get to 90. Okay, so let's pop back over and look at this. really what's happening is it looks kind of like a cubic graph, like x to the third. It's just instead of continuing on to the right, there's an asymptote there. So there's actually a vertical asymptote at 90. Okay, so picture what's going on. I got 0 degrees, 30 degrees, 45, 60, 90, and remember tangents like slope. Well, the slope of a vertical line is undefined. Okay, what happens if I go to here, like at 120 for instance? Well, at 120 the slope switched to negative. It still has that reference angle of 60, so 120, also known as 2 pi over 3. So since it still has that reference angle of 60, it's going to be just like 60, only it's going to be a negative square root of 3. So negative 1.732. Okay, so if I continue on over here, so this would be 120, I'm going to be at negative 1.732. It's going to be something like this. Okay. Okay, so what I need you to see here is that this graph is going to start having the same values, only they're going to be the negative version of these. Okay, and then at 120, now this is going to get a little cluttered because of my table here. So I'm going to go ahead and go over to the graph, the calculator for just a minute. Okay, and so here are those same values. If I go to 120, 120 had the negative 1.732. 135 is where the reference angle is 45. Okay, it's at negative 1. So I'm still seeing those same values again, and that should be no surprise. Okay, I'm going to push graph. Now, do you understand I'm doing zoom 7, which is a Trig screen, and this is what's going on. Okay, now, I happen to be in degrees. This spot right here is 90, also known as pi over 2. This spot right here has a reference angle of 90, 270, 3 pi over 2. This spot right here, negative 90, negative pi over 2. And one more asymptote showing, negative 3 pi over 2, all negative 270. Sorry, I got my pattern going there. Okay. Other points of interest here, I'm not going to do every single point there is, but what I want you to see here is that at 45 we're at 1, and those are going to be key points that we're going to hone in on because they're easy to spot. Okay, so pi over 4, tangent of pi over 4 is 1. Tangent of pi over 2 is undefined. Tangent of 0 is 0. These are specific points that I need you to just know. And then what we're going to do is build graphs off of those values. Okay, so just kind of know that that's what's going to happen. Okay, so I want to go back and do a tangent graph again. I just want to do it without, let me clone. Okay, and then we'll clear it. Okay, so again, what we're going to do is y equals tangent. And this is how I kind of expect things to go when we're in class. So you don't have to, you know, do this giant table of values. That table of values thing was just so we could establish a shape. Okay? All right, so here we go. I'm going to call this pi over 2. That's where the first asymptote is. This will be 3 pi over 2. Okay, and this will be negative pi over 2. Okay? Tangent of 0 is 0. Tangent of 45, also known as pi over 4, is 1. So I'm going to call this 1. Call this negative 1. And tangent of 90 is undefined. Tangent of negative 90 is also undefined. Tangent of negative pi over 4 is negative 1. Excuse me. And this is one cycle of tangent. Now, one of the things I need you to notice here is that one cycle happens to be in the difference between pi over 2 and negative pi over 2. So that change is actually pi. Tangent starts repeating in 180 degrees. Okay, so for tangent, the period is pi, or 180. For tangent, the period is pi over b. Okay, so if there is a number inside with x, this is a big change between sine, cosine, and tangent. This one is about 180 or pi instead. Okay, so if that's true, then this whole thing repeats again. So pi to the right of 0 should be the same value. If I go, if this was pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Well, from pi over 4 to 5 pi over 4, I know some of you are going to hate this. Sorry, that's a 4. To 5 pi over 4, that distance is 4 pi over 4, also known as pi. In other words, it should have the same value. So over here at 3 pi over 4, and basically it's just copying that shape. So here I have one below, at 0, at 0, at 1, at 1. I have an asymptote, I have an asymptote. Okay. Oops, sorry, wrong button. Sorry, a little bit of a cough going on this morning. Okay, so what else? So period for tangent, 180. Amplitude? Well, amplitude, remember, is max minus min over 2. Well, the maximum is infinity. Minus the minimum is negative infinity. This is kind of silly. So this is 2 times infinity divided by 2, which is infinite. All right, well, that's just kind of silly. So amplitude, because there is no actual number, remember infinity is not a number, it's a philosophical idea, there is no amplitude. Now some people are going to actually say infinity, and I will accept that, because it's infinitely high. Half of infinity, half the height, half of infinity, whatever, it's still infinity. All right, so but my cute little math there is, I think, interesting, if nothing else. Okay, so amplitude, infinite or none. You could say not applicable if you prefer. Period, 180. Now there's no phase shift or vertical shift on this graph because it's a parent function, but they work the same way as with sine and cosine. Okay, domain, range, and unfortunately we have vertical asymptotes that go with this. And as you know from before, domain and vertical asymptotes go together. Well, let's do range next because that's super easy. Range for this, all real numbers. Woohoo! The domain is basically not the vertical asymptotes. So vertical asymptotes are x equals, well, the first one is at pi over 2. The second one is at 3 pi over 2. The next one would be at 5 pi over 2. The problem is that I can't list them all. They're an infinite number. They keep going. You know, as with any periodic function, it keeps going forever. So we're not going to write it like that. We're going to write it like this. Pi over 2 is the first one, plus, how far apart are they? Well, remember the period for this is pi, and it takes pi to get to the next one. So what I'm going to do is say times pi k. Now this k, you don't have to write anything about this k, but it is assumed to be an integer. In other words, a whole number, positive or negative or 0. And so the idea is, if k was 0, this would just be pi over 2. Pi over 2 plus pi times 0. If k was 1, it'd be pi over 2 plus pi. If k was 2, it'd be pi over 2 plus 2 pi, which would be the 5 pi over 2. If k was negative 1, pi over 2 plus pi times negative 1 would be this negative pi over 2. So this is a good way to write it. It's not the only way. We could say that it's pi over 2 times k, but if we do that, that includes the even k values, odd or even, and we can't do that, so we have to write a little note saying k equals odd integer, and we'll just say odd, and an integer will be implied. Okay, well, this is a lot of time spent on this. again, these values are going to work the same way. Domain is going to be x not equal to whatever those asymptotes were. Oh, I didn't put asymptotes in my list. Okay, and we already wrote this, so I'm going to be really quick about it. Range, all reals, no amplitude, pi for period, and that's it. Okay, what I need to do now is do something very scary. And that is, well, I'm not going to do that because time is an issue. I'm going to do that. Okay, so quick little reminder here that cosecant is the same thing as 1 over sine. And so I'm going to be just a little bit clever. Okay. So what I'm going to do is actually graph sine first. Okay. So in blue, and I know color might be an issue on the picture here, I'm going to graph sine first, and I'm going to do this the same way we typically do. So, and I'm going to call this 2 pi, and I'm going to go over here to negative 2 pi. And again, I'm graphing sine. Now, I'm not going to have time to do this for cosine and secant, so just understand that we can play around with it in class, but the concepts are the same. Okay? So this is sine. This is not the graph I really want to graph. This is really the reciprocals of the graph I want to graph. Okay? So what I'm going to do, sine x and then cosecant x. Just some quick little values to okay, get off of there already. Stop it. All right, whatever. Okay, so just a reminder, 0, 30, 45. Okay, and what I'm going to do is do 3 columns here, and we're going to talk about y values. Okay, so I'm going to kind of just throw these in for a second. Okay, and those are the sine values, just from 0 to 90, and we're going to use this as a teaching tool here. Okay, all right. So if I'm going to do the reciprocal of sine, 1 over sine, then this column would be the reciprocal of these y values. So I'm going to do 1 over 0. Yep, sorry, that's bad news, isn't it? 1 over 1/2. 1 over the square root of 2 over 2, which is really just the square root of 2, about 1.4-ish, 1.414. And this will be 2 square root of 3 over 3, sorry, which is approximately, I don't know. And then the reciprocal of 1 is 1. Okay, so let's graph these new y values. Okay, so for that same x value of 0, I need to do undefined. Well, you know that that looks like an asymptote. Reciprocal of 1/2 at 30 degrees. So now, just a quick little note here. If this is 90, then 30 would be a third of 90. Okay, so that's going to be at 2. And then 45 is the square root of 2, so 1.4-ish. 2 square root of 3 over 3, it's about, I think it's about 1 point, I don't know, it's 1 point something, whatever, we'll skip it. And then 90 is at 1. Now these values are going to repeat on the other side, because that's how this works. And then notice the reciprocal of 0 again is undefined. If I sketch that in, this is what it looks like. That is probably not surprising, or that is not obvious. And then this piece is going to look the same. The reciprocal of 1 is still 1. And then it's going to go this way because these numbers under here are all negative. So when I do their reciprocals, they'll still be negative. Everywhere you see a 0, it's going to be an asymptote. Everywhere you see a high point, it becomes the bottom of something that looks kind of parabola-ish. Something like that. Well, that's it. That's the look. Okay, now let's pop over the equation on the calculator, or the graph on the calculator. All right, so this is sine. You know what this looks like. There it is. Okay, Going to do the same thing over here, only now we're going to do 1 divided by. Now I have this set up so it's going to graph it thick. Okay, it has that little thing on all the way to the left of Y2. It's extra heavy, it's like bold. Okay, so when I hit graph now, it's going to, the sign I think will already be there, and then we'll be seeing 1 over sign, also known as cosecant. And there it is. Now remember, your calculator does not show asymptotes. Well, unless you have like an old 83 or maybe even one of the older 84s. Calculator's trying to connect things it's not supposed to, and you need to understand that it's really not there. Now also, one other quick little note. Sine is really not part of this graph. We're just using it as a guide. And that's how I always do these. Okay. So for instance, let's do one more fairly quickly. Let's do y equals 2. Let's do secant this time of 3x. Okay. So what I'm going to do is the first graph I'm going to graph is cosine, and I'm just going to do a little sketch of cosine. And again, cosine starts at the top, it ends the cycle at the top, in the middle it's at the bottom, so this would be 2 pi. Okay, so again, this is just straight up cosine. Okay, and it looks something like these. Okay, I'm going to do another one. Now I know this is going fast. You can rewind, you can pause, you are in control. Okay, so this is cosine. Okay, the next graph I'm going to graph is y equals secant. So this is the reciprocal, and this is the order it would happen. The reciprocal of cosine is secant, so also known as 1 over cosine. So that means all of the y values on this red graph, the graph that's dotted there, the graph that I just did, all of those y values, I need to do reciprocals for the same x values. Okay, so for instance, the reciprocal of 1 is 1. The reciprocal of 0 is undefined. The reciprocal of -1 is -1. The reciprocal of 0 is undefined, etc. Okay, and now the idea here is if starting at x equals 0, as these red y values get smaller and smaller and smaller, their reciprocals are bigger and bigger and bigger. Similarly, so this has the same shape as cosecant, it's just it starts in a different spot. Just like cosine has the same shape as sine, it just starts at a different spot. Now I know some of you, this is going to bug. So if you feel compelled to tack on another, oh, I didn't want that in red, oh well, another asymptote, and you want to finish that little guy, you betcha. So I've really done a little more than 2 cycles here. Okay, remember each cycle has to have a top and a bottom. So there are 4 little chunks. Okay, all right, well we didn't answer any of the questions that go with this, like you know, domain and range and all that kind of stuff. So let me kind of just buzz through those questions. Okay, for this particular graph, it's much like tangent. The first asymptote is at pi over 2. So x can't be pi over 2. The asymptotes are separated a pi apart. From here to here is pi, because 4 squares is pi. Okay, plus pi k. Range, a little different. Remember that none of the middle is here. Okay, none of this is here. That's all gone. Okay, remember that it's just the green graph of secant. Sorry, I just felt compelled. Some of you know what that was. Okay, so it is, the y values are greater than or equal to 1 and less than or equal to -1, and I need an or in the middle of that. Okay, and I'm going to have to come back and fix this in just a second. Asymptotes are x equals pi over 2 plus pi k. Now all of this is for secant. I haven't done the 2 and the 3 yet. Okay, and time is going to, I know, people are going to be yelling at me. Sorry. And then, is that it? Asymptote, or amplitude rather? Sorry, none, or infinite if you prefer. Period, well, right now it's 2 pi. Okay, so let's fix this now, because this says we're supposed to multiply by 2. Oh, let's go to blue, I guess. We're supposed to multiply the y values by 2. Well, this used to be 1, so now it's 2. Scale change. A full cycle was supposed to happen, originally it was 2 pi, now this will be 2 pi over 3. That's it. Okay, so period, 2 pi over 3. And I will just tell you now that phase shifts and vertical shifts for this, because of asymptotes, get to be a huge, huge, huge mess, and we're not going to do them. Okay? So if it has asymptotes, we're not going to do it. All right. So do spend time practicing with these. This is ugly, and I know the asymptote domain stuff is probably the ugliest stuff. Okay, so spend some time, rewind, go back through this. This was kind of quick, and I'll see you in class. And SanfordFlipMath, we are out.